All right, class. Today we will be talking about colligative properties, which is a property that depends on the number of particles dissolved in solution, not the type of particle. First, we will have boiling point elevation, where the boiling point of a liquid will be higher when another compound is added. Here's our formula. And then we've got a practice problem right here. We'll also need to know that molality equals moles of solute over kilograms of solvent. So, what is the boiling point elevation of a solution in degrees Celsius made by dissolving 50 grams of CaCl2 and 0.5 kilograms of water? The normal boiling point of water is 100 degrees Celsius, and the Kb for H2O is 0.51 degrees Celsius per molality. So we know we have 50.0 grams CaCl2. So if we calculate the mass, the molar mass of CaCl2, we know it's 111.1 grams for every 1 mole of CaCl2. For 3 moles of particles, 1 mole CaCl2 equals 1.35 mole of particles. So we have our moles of solute here. We can put that into the equation right here and get molality equals 1.35 mole of particles over 0.5 kilograms of solvent. And from this, we get 2.7 molality. This is our molality here. We can now use the molality of the solution in this formula. We have the constant that is 0.51. It's given in the question. So we've got change in boiling point equals, this is our constant, 0.51 from right here, times 2.7 from here. When we do this, molal will cancel, and we get 1.38 degrees Celsius. This is the increase in boiling point, so we'll have to add it to the original boiling point of water. So we get 100 plus 1.38 degrees Celsius equals 101.4 degrees Celsius. And that's our final answer. Next, we can go to something that is similar to this topic, but the opposite, called freezing point depression, which is known as the freezing point of a solution will be lower when another compound is added. And this is the formula we'll be using. Change in freezing point equals molality times the freezing point constant. We've got a practice problem here. What is the freezing point depression when 62.2 grams of toluene is dissolved in 481 grams of naphthalene? The freezing point constant for naphthalene is 7 degrees Celsius per molality, and the freezing point of naphthalene is 80.3 degrees Celsius. We'll use the same formula from earlier for molality equals mole solute over kg solvent. So we know we have 62.2 grams of C7H8. For every 1 mole of C7H8, we get 92.14 grams of C7H8. This is just the molar mass of toluene, which gives us 0.675 moles. So our molality will be molality equals, bring this on top into this equation. So moles of solute is 0.675 moles over 0.481 kilograms of solution, which gives us 1.4 molality. We'll then plug it into this equation. So we'll get change in freezing point equals 7 degrees Celsius per mole times 1.4 molality equals 9.82 degrees Celsius. So the freezing point of the new solution will be 9.82 degrees lower than the original. So we have to take the original 80.3 degrees Celsius minus this number, 9.82 degrees Celsius, equals 70.5 degrees Celsius. This will be our final answer for this practice problem. And that is all for freezing point depression. Then we'll move on to osmotic pressure, which is known as the minimum pressure which is needed to be applied to a solution to prevent the inward flow of its pure solvent across a semi-permeable membrane. Our practice problem will be 2 grams of unknown protein is dissolved in 0.1 liters of water. The osmotic pressure was 0.021 atm at 25 degrees Celsius. What is the molar mass of the protein and the weight achieved, or the height achieved by the solution? We'll have, this is our formula, MRT. So here we'll have 2 grams of solute from right here. And then the constant we'll be using is 0.0821 times temperature in Kelvin. All divided by the osmotic pressure of 0.021 atm times the volume of the solution. We'll assume that it is still 0.1 liters. From all of this, you will get 2.33 times 10 to the 4th grams per mole. So this will be the final answer. This gives us the molar mass of our protein. Now we can use this to get the height achieved by the solution. But we won't be calculating the height acquired of osmotic pressure problems in this class, so we'll just move on to vapor pressure lowering. So for vapor pressure lowering, it can be defined as the vapor pressure of the solution is lower than the vapor pressure of the solvent. For this topic, we have a practice problem of calculate the vapor pressure of water at 90 degrees Celsius for a solution prepared by dissolving 5 grams of glucose in 100 grams of water. The vapor pressure of pure water at 90 degrees Celsius is 524 torr. So vapor pressure of the solution is equal this is Raoult's law. So vapor pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. Mole fraction of the solvent is equal to moles of water over moles of water plus moles of glucose from this problem. So we'll have to get the moles in order to calculate the mole fraction. For water, we have 100 grams of water divided by 18 grams per mole, which is the molar mass of water. So grams cancel. Which equals 5.55 moles. And then we'll need to finish this problem here, we will need to add, to get the denominator, we'll add the molar mass of glucose, which would just be, we have 5 grams of glucose. So it'll be divided by 180 grams per mole, which is the molar mass of glucose. And we get 0.278 molarity. So we'll have 5.55 molarity over 5.55 molarity plus 0.278 molarity. So the mole fraction, this will give us 0.96. To get the vapor pressure of the solution, we'll go back to this, plug this in, do 0.96 times 524 torr, which will be equal to 503 torr. Done.